encouragement from their opening remarks. So we are also going to introduce our guest speaker for today. So for our engagement today, the guest speaker that we have is Mr. David Otokin, who is an expert in geomechanics, a part of Haliburton, Nigeria, and he has several years of experience in pressure predictions and wellbore stability analysis. And he is going to take us through the presentation today. He is an alumnus of the University of Ado-Ekiti and University of Nigeria in Nsukka, and he is currently pursuing his PhD in geophysics at the Federal University of Petroleum Resources in Efron. He has an MBA in Quantic School of Business of Technology and Technology, United States of America. This is a brief summary of our guest speaker. And when he comes on board, just as we have said, as an expert in pressure prediction, he's going to take us through the topic of discussion today, which is in geomechanics. And I want to assure you that it's going to be a good time that we're going to spend with him. So, for our engagement, we want to set some ground rules that is going to guide our meeting. So, for all of us that are joining virtually, we request that when you join, you quickly turn off your video and also mute your mic so that you do not disturb our meeting. So also, we want to request that whatever question that you have for the presenter, you need to put it in the chat room, or we give you the opportunity to, by raising up your hand, after which we are going to call you so that you can make your comment. That is what is going to guide our meeting, and we hope that everybody is going to adhere by these rules that we have set for ourselves. So before we commence the presentation, it's our culture in NAPE to always give honor to whom honor is due. So because of this, we want to recognize the presence in our midst this morning, the Vice President, Mr. Tony Wukoma, for gracing our meeting. Thank you so much for coming. And also want to recognize the presence of our President-elect, Mr. Elliot Ibetu, for finding time inside of his tight schedule to also join this our meeting. Thank you so much for coming. All other people in this meeting, and the management staff from the Fund IDSL and MPDC, we really appreciate your honor in this meeting this morning. And we want to progress the meeting. And on this note, I want to invite Mr. George and David to take over the presentation.
Okay, good morning all.
Yeah, good morning, David.
Okay, good morning all. I want to use this opportunity to appreciate the entire leadership of NAPE Benin chapter for this opportunity. I want to acknowledge the presence of the President-elect, as well as the current Vice President of NAPE. Please permit me to stand on all existing protocol, even as I move to the presentation of today. All right. Above is the outline of the presentation, and it's my target, is my desire this morning that in the next 30 minutes, I'm going to turn everybody here present to a geomechanics enthusiast, starting from introduction and to the subject of Wellbore instability, down to the tool the most prolific and the most renowned tool for pore pressure prediction. Okay, I said I will be defining the basic terms of geomechanics, highlight the root cause of geomechanics, and to how we can diagnose Wellbore instability, and as well give some recommendations towards safe drilling practices. All right, when we are talking about Wellbore instability, we are talking about the undesired condition. When we are drilling a hole, we have the wellbore size, and we now have an undesired condition in which the wellbore size becomes enlarged. When we have this undesired condition, it gives us some drilling challenges. And when we have this condition, we call it wellbore instability. And there are certain factors that can result into wellbore instability. It can be classified into controllable and uncontrollable. Some of these factors, root cause of wellbore instability, are technical error, man-made, such as a wellbore trajectory, such as overpressure, and other factors that are avoidable, that maybe as a result of our planning we introduce into drilling. Okay, the other factors that are beyond our control, they are natural factors that could result into wellbore instability. Things like tectonism, things like faulting. When you talk about the fault, the in situ stress of the rock, when you are talking about the fault regimes that we are drilling through, if you are drilling through a fault zone, is already a weak zone in itself. So there's nothing you will do other than for you to plan how to mitigate the severity of the challenges you'll be having in it. So wellbore instability can be classified into two. Some people classified it into chemical and mechanical. But my focus this morning will be, how are we going to be able to address wellbore instability? I know this is not a training, this is a technical section, so I'm not going to go into every damn detail of everything. But Dawson and Dawson carried out a survey in the year 2007, which was reported by Caripodi. And in this survey, it concluded us that 44% of non-productive downtime associated with drilling is as a result of wellbore instability. This has been estimated to say that to cost the industry year in, year out, a whopping sum of 8 billion naira. One wouldn't have been so much concerned if maybe from 2007 to date, if we have been able to do things about it and we've been able to reduce the effect of wellbore instability to something like 20%, we'll say, oh, we are doing fine. But somebody that had the opportunity, my activity, I see drilling reports and I review drilling reports, and I can still attest to the fact that to date, if once you quantify, if another survey should be carried out, we will still be having something within the window of 40 to 50% challenges associated with wellbore stability, resulting into non-productive downtime. So this called to mind that we have not been addressing it well. We know the challenges there, but we need to address it, and that's the reason for a presentation or sections like this, to say that we need wellbore instability because it's a challenge. It's costing we can't continue like this. All right. But when we talk about geomechanics, the origin of the geomechanics is applicable throughout the entire lifespan of an asset, from exploration till abandonment. And if you look at my chart, the touch to the right-hand side, I've tried to highlight some of these challenges that geomechanics can help us answer. Some of the questions that a typical geomechanical model can help us answer. One of it is pore pressure prediction. You want to know the amount of the pressure in your formation as you are drilling, so that when you are drilling, you drill over balance and be able to drill smoothly without having a kick. And you want to know the the fracture grade and the minimum horizontal stretch of the rock so that you don't begin to have losses. If you look at to the right-hand side, you see something like drilling optimization, sand production. Geomechanics will help you to know at what is the optimum drawdown for your reservoir before you begin to produce sand. Sanding is a major problem to production. As somebody who has done production for a few years of my life, I know what it means when your reservoir begins to produce sand. Fourth seal and fourth seal integrity reactivation. Part of the practice we do in the industry is to re-inject some of our waste product, or as a way of maintaining reservoir pressure, we re-inject gas or water into the reservoir. We want to know what is the integrity of the seal, of the shale formation that is serving as the seal or your cap rock that you are injecting into. Otherwise, you'll be injecting into one reservoir thinking you want to maintain the pressure, and the pressure will be getting lost along the fault, and it will be transmitted into another reservoir. It can even help you, it can even result into water coning. So you want to, a typical geomechanics will help you to answer some of these questions and narrowing it down to what we are looking at today, which is Wellbore instability. When we have a typical geomechanical model will help us to know what is the required mud weight to avoid Wellbore instability. What's the origin, what's the root cause of Wellbore instability? Our earth model is like the picture to the left-hand side. Is subjected to stress. And when you are drilling through it, what we are doing is we are boring a hole into the earth model. And it's like you are having a stadium pack of jam-pack of people, and all of them are touching each other shoulder to shoulder. Just imagine if you have an helicopter or you have a drone that you can use to lift one of them at the center. The stress that the person to the left and to the right is exhibiting on the person that was removed will be redistributed around the void. So when we are drilling into the subsurface formation, we are creating a void and we are disturbing the stress regime around the wellbore. And when we are distorting this stress regime, the hoop stress along the wellbore is what we need to balance. So the stress that is generated as a result of us evacuating or boring a hole into our earth formation is what we need to use our mud weight to counter. And if we don't know what is the hoop stress around our wellbore, we will not be able to drill successfully. That's the main reason why we usually have wellbore instability. So, and this is something like I've mentioned that our geomechanical model will help us provide an answer to. When we talk about a geomechanical model, what do we mean by a geomechanical model? Components of a typical geomechanical model. Okay, a geomechanical model is made up of three things: your formation pressure, your field stresses, and the rock properties. Your field stresses is made up of these highlighted 4 parameters that, if you look at the image to the right-hand side, you have your vertical stress, the 2 horizontal stresses, their orientation, and their magnitude. So when we are building a geomechanical model, we want to know what is our overburden, which is the vertical stress. We want to know the minimum horizontal, the maximum horizontal stress. We want to know the orientation. We want to know the formation pressure. When we marry these 3 things plus the rock properties and bearing in mind the trajectory of the well, all these parameters now join together to form what we call a geomechanical model. But a geomechanical model that is not calibrated is best a model. So the other aspect of wellbore instability or wellbore analysis is the analysis itself. A well has been drilled through our subsurface, and the well has communicated to us what it was, why it was being drilled. So we want to now use the information that we have gotten from the drilling activities to calibrate our model. When we calibrate the model, we will now know the optimum mud weight, which is the output, the optimum mud weight that will help us to prevent shear failure, or the optimum mud weight that will help us to prevent tensile failure. So, capping it, summarizing it again, a geomechanical model is made up of three things: formation pressure, your field stresses, your raw properties, and you now bear in mind the trajectory of the well. When you combine all this together, it gives you the optimum mud weight needed to drill without wellbore instability. I'll just go through each of these items briefly. When we talk about pore pressure, you're talking about the pressure within our pore spaces. And when you are trying to build a model, the pore pressure, we assume the theory, according to Terzaghi, is that compaction increases with depth. And as compaction increases with depth, your porosity is supposed to decrease with depth. So when you now have porosity being preserved as a result of under compaction leading to your the overpressuring of your formation, the best way to do it is to establish a trend through the interval that compacted normally, like you can see to the image to the left-hand side, and a reversal, a deviation from that trend, which is this my dotted blue line. A deviation from that dotted blue line will be calibrated using any of the available model to get what the formation pressure is, which is the second image at the center. So if you look at the third image towards the right-hand side, you now see a typical porosity indicator, which is our sonic. You can either use your sonic, you can either use your restivity. This is restivity rather. You can either use restivity, your density, your sonic information, or your velocity. When you incorporate that into an analytical model, it gives you a prediction, like you can see to the left-hand side, which is the red line, which is our model. Like I mentioned earlier, the model will be calibrated to measured information. In this instance, it was calibrated to mud weight and the RFT. So it will be calibrated, and when it is calibrated, you note the calibration that gives you a good match. And that with that, you can now incorporate that into your planning. Okay, going into the stresses, Anderson classified the stress regime into three. We have your normal for thin, your stride slip, and thrust fault. In Niger Delta, we are in what is called the typical normal fault regime. And when you are drilling in the normal fault regime, part of what you want to call to mind is what direction is best when I'm drilling an horizontal well. If you are drilling a vertical well, you know you are drilling a vertical well. If you look at this image where my cursor is to the left-hand side, you see the direction of the minimum and the maximum horizontal stress. The maximum horizontal stress is going towards the northeast, and the minimum horizontal stress rather is going towards the northeast. That is the red line. The maximum horizontal, the maximum is the red line going towards the northeast. The minimum is the other one going to the between the southeast. So when we are drilling, what we want to do is we want to balance the effect of the differential between the two horizontal stresses. The next chart to it give us some value to help us narrow down this point. So assuming your vertical stress is 10,000 PSI, your maximum horizontal stress is 9,000 PSI, and your minimum horizontal stress is 8,000 PSI. When you are drilling, you want to balance the effect of the differential. So the differential, if you are drilling towards the direction of the maximum horizontal stress, will be 10,000 minus 8,000, and that will give you the differential of 2,000. When you are going in the direction of the minimum horizontal stress, the differential in that instance will be the differential between the maximum horizontal stress and the vertical stress. And that will be 10,000 minus 9,000. So if I decided to drill in the direction of the maximum horizontal stress, I have 2,000 PSI to battle with. Why not just go in the direction of the minimum horizontal stress? That's what geomechanics is saying. That drill in a normal fault regime, your best direction is to go in the direction of the minimum horizontal stress. Because in that instance, the differential between your maximum horizontal stress and the vertical stress is minimal. And that is the most stable direction to drill. Okay, the chart to the left, to the right-hand side gives us a summary of parameters that we use in building our model and where we get them from. For our vertical stress, that can be integrated from density log, your minimum and the maximum, or your minimum horizontal stress, the magnitude can be gotten from your LOT information, extended Likov test or mini frac. But when you are dealing with the orientation, the azimuth of your minimum horizontal stress or your maximum horizontal stress, you got them from your forehand caliper log, you get them from your image log. Your maximum horizontal stress, the magnitude you need to build a model to get that one. And your pore pressure, I've spoken about that one. The rock strength, which is the elastic parameters of the rock, that one will be gotten from the lab. You take a core sample, you take them to the lab, and you subject them to stresses. And from there, you are able to get the magnitude of your elastic parameters. When we get the magnitude of our elastic parameters, which is the third parameter in a typical geomechanical model, you get them as example of them is all this, the blue dots on the last plot here. When you have your CO, which is your cohesive strength, where that one has been derived from the core sample, and you now build a model. When you are done building your model, you now calibrate it like it was done in this instance. You calibrate your model to the parameters that was taken from the lab. When we have all these input of a geomechanical model, you now bring them all together to now get your shear failure gradient. I'm not plotting a line of shear failure gradient. What I have displayed up here is what we call the Steronoise plot. Steronoise plot, or so for your Steronoise plot is giving us the direction of the minimum horizontal stress. Like I mentioned the other time, the best direction to drill when you are in normal stress regime is your direction of your minimum horizontal stress. And the perpendicular to it is the direction of your maximum horizontal stress. Around it, it will be showing you that, oh, if you increase your inclination, I mentioned earlier that part of what you consider is the trajectory. So if you increase the inclination of your Wellbore, the center of it is 0. If you move to inclination of 30. If you increase it to 60, for example, it's telling us that the moderate you will need to drill at that depth, it will be something within this red. So I go to my what's it called? The key for me to read off what the value will be. I'm saying that this red is within the range of 10.2. So it's telling me that for me to drill that depth successfully, I need a mod weight of 10.2 ppg. If I change the azimuth and I'm not drilling in this azimuth, you can see the azimuth is coming from 0 and it's going around the circle. So if I'm still drilling at inclination of 60 degrees, but I am drilling at the azimuth of 180 degrees, it's showing me that I will fall within this green line, which falls within the direction of minimum horizontal stress. So it's telling me that for that, I will need pore pressure of a mod weight of 9.8 ppg, a little bit lower than that of the azimuth of 60 degrees. So this is to tell us that you don't just say, oh, we drill a well and the last well we drill to inclination of 60 degrees and we did not have any problem. The azimuth also matters. And that is why geomechanical model is your best bet answer, because it will factor in both the inclination, the azimuth, the raw properties, and it will give you a good result. A typical geomechanical model will define these parameters for you. Will define your pore pressure, and will define your fracture pressure. This we call it safe window. Safe in the sense that if you place your mud weight anywhere within these two boundaries, you are not going to have a kick, you are not going to have losses. But that doesn't mean you will not have Wellbore instability. What some engineers, some drilling engineers would love to do is that, oh, we have drilled a well through this fourth block before. We know our pressure. We can drill. Yes, you can drill, but I can tell you also that you will run into Wellbore problem. So another parameter that is of key interest that will save you of money and time is your shear failure gradient. So a geomechanical model will define for you your shear failure gradient and will define for you the minimum horizontal stress. When it gives you the minimum horizontal stress and your shear failure gradient, then you factor in your uncertainty, which is the reason why they usually in the industry, they put 0.05 ppg. So you factor in your uncertainty and add it to your model, then it gives you your stable window. So this stable window, if you have this defined, it will help us give us the following benefit. One, like I mentioned, it will tell you the parameters of the rocks, but most especially, it will help us to minimize costs, which is the way I started my presentation from, that it will help us to minimize the non-productive downtime. It will help us to minimize costs. It will help us to optimize the well path. You will know that, oh, if I go along this azimuth, I'm going to have this drilling problem. Okay. This is a real life case scenario. We have a case study here in which a client drilled 10 wells. Of the 10 wells that was drilled, 4 of it was lost. And in all of the 10, they experienced top pipe. We reviewed the model, we reviewed what was the challenge, why the well failed. And part of the background into our review is that the well was, all the wells are deviated, highly deviated, maximum of 60 degrees. But we realized that what they did was they built a pore pressure frag gradient model, but they did not build a geomechanical model. So when they were planning the well, they planned based on pore pressure model alone. So if you look to the plot to the left-hand side, you will see your caliper log. My caliper log is showing me all those red places, is showing me washouts, showing that the well from the interval displayed from the beginning to the end are all washout. And that was the reason why they were having instability. Why did they have that Wellbore instability? They planned based on pore pressure. So when after the post-mortem analysis that was done for this well, reveals that the mud weight that was used is below the required shear failure gradient. Is below the shear failure gradient, meaning that they should have, if they have used mud weight above the shear failure gradient, like I displayed in the last chart, they will have drilled successfully without losing the well. They will have drilled successfully without having Wellbore instability. Based on this, our recommendation is this: Wellbore stability analysis is a must do. It should be a standard practice for every of our deviated well. If you are drilling any deviated well, Wellbore stability analysis should be part of our drilling practice. This is what we have not been doing in the industry. And that is the reason why we keep having stock pipe, we keep having losses, severe losses. At the end of the day, we thought we are penny wise because we thought we wanted to save costs from building a geomechanical model, but we realized that we are penny wise, pounds foolish, because $8 billion per annum is still a huge amount. Okay. Halliburton came up with this chart and they said the indicators of Wellbore instabilities are as follows. I'm not going to go into each of those indicators. I just want us to see our objective is to drill a stable well. And when you are having your cuttings at the surface, when you are looking at the cuttings from a stable well, it should have beat mark, because beat is what is drilling for us. They say when you see something like this and it's showing a clear evidence of beat marks on them, happy driller. I'm not just saying happy driller alone, happy geomechanics analyst. Because both the geomechanics specialists and the driller are happy that the hole is performing well. But when you follow my cursor up a bit, you now begin to see what they call cavings. When you begin to see cavings, and some of them will be angular, some of them with edges around them, it's beginning to tell us that we have started having shear failure. And if nothing is done about this, we'll run into problem, we'll get stuck. So immediately you begin to see cavings is an indicator of something. I'm not saying all cavings are as a result of Wellbore instability. So, but I am saying cavings is an indicator of something. But when you begin to see them in numbers and in volumes, then it's telling you this is shear failure. When you see the topmost hole size, the indicator of it at the surface is what we call the splittering shades. They have sharp edges. It's showing us that we are drilling into overpressure zone. Something is pushing it. It's like a man that is standing by the pool, and all of a sudden somebody push him into the water. In his mind, he will be shouting, "Who pushed me?" That's the way these cavings are saying, "What pushed me into this hole?" The geomechanics analyst on board will be saying this is pressure pushing itself into the well. So that is an indicator of an overpressure zone. And the other one is when you are drilling through rubble zone, when you are drilling through fractures, naturally existing fractures, you will be having rubble cavings like this. And the last one of it, this one you don't see it at the surface. This one I don't pray you see it. I don't like it. It is what we call well ballooning. It means you have drilled with a mud weight that is higher than what is needed. You have drilled with a mud weight that is higher than the minimum horizontal stress. And as a result of that, you have tensile, you have what they call tensile failure. You have fractured the formation and you begin to lose into the formation. And after you have lost enough for your mud weight to now reduce and it's now under balance, you now begin to take in again. And this cycle will continue and continue. Cycle of wear control. Okay, so like I mentioned, I'm not going to read through all the indicators, but the indicators of Wellbore instability at the surface include high torque. Something is resisting your friction, or the friction of your drill string. So when you have a high torque or you have a high drag, is indicator of Wellbore instability. When you have hole fields after taking a trip, you are not drilling, but all of a sudden your hole is backfilling. It's telling you that the cuttings are coming from somewhere. All these things are indicators of Wellbore instability. Okay, to bring it to a close this presentation, I'm going to just highlight some of the recommendations that will help us to drill, because these are the things we need to address if we want to avoid or if we want to get free from Wellbore instability. One of it is what I have mentioned. Geomechanics Wellbore stability analysis should be part of your drilling program. All our deviated wells must include a typical geomechanical analysis. Let's analyze it. Let's look at what the well communicated, all the wells around that have been drilled in that field. Let's look at what the well communicated to us, and we'll pick lessons from them, and we use it to build a model to plan the prognosis well. That's number one. Number two, a typical geomechanical model will help us to optimize our casing seats. Will help us to know, okay, this is where we are supposed to set casing. From your geomechanical model, will you know that where you had losses in the previous well, and as a result of that, you will know whether you want to case that section before you go into overpressure zone, so that you don't get into overpressure zone and you are at an attempt to prevent from well control angle and attempt to prevent kick, you now started having losses at the shallow end. And when you have so much losses, you take a kick at the deeper section. So Wellbore stability analysis will help us to optimize our casing point selection. Part of our recommendation is drilling practice. I know, and kudos to our engineers, to our well planners, when they are planning our wells, they usually incorporate torque and drag analysis into their planning. And when they do this, they analyze the optimum flow that is needed to bring out the cuttings. They look at it, the ROP, and what the volume of cuttings that will be generated before they decide the optimum flow. But when we get into drilling, it is difficult, I know. Operations are not like model, but as much as possible, we should optimize our drilling practices so that we don't now drill beyond what was model. The model look at it and say, oh, this is the optimum flow that will help us to bring out the entire cuttings. If we not increase ROP and we did not increase flow, or we did not go back to our model to go and optimize what will give us, or to go and analyze what will give us an optimized flow that will bring out the cuttings, we're already introducing problem into it. So, and if we are not cleaning our whole well, which is part of the recommendation, good hole cleaning. If we are not cleaning our whole well, we are already trending towards a stop pipe. Okay, another thing that should be part of our recommendation, that's part of our recommendation, is optimization of our trajectory. Part of what we look at, what we look into when we are trying to decide what is the best trajectory is we look at the fault, we look at the azimuth of the maximum and the minimum horizontal stress. We even look at community relation. If you already have a well located in this community and you have settled that community, and the azimuth is saying, oh, let's go to another community, we have to go and put, for you to achieve this azimuth, you have to go and put it in another community, and you are looking at community relation in terms of how much you need to settle them. That is a factor, but don't ignore one. All the factors must be looked into critically. So we must optimize our trajectory in our well plan by looking at the maximum and the minimum horizontal stress, so that we will not be introducing well control or wellbore instability into our plan. Okay, another challenge in drilling is drilling through faulted or depleted zones. Depleted zone, if you are drilling through a zone that is having an elevated pressure or an overpressured zone, and you are going from that overpressure zone, because when we are drilling in field wells, we are drilling through some of the reservoirs we are drilling have been depleted. When you are drilling through depleted zones, you want to now plan for how are you going to drill through these depleted intervals. And one of the things that can help us is the stress gauging method of loss control. You get these stress gauging additives, different sizes, introduce them into our mud, plan them as part of our planning, so that when we are drilling through depleted zone, it will help us to seal all those depleted intervals and we will not be having losses through them. Some of these stress gauging additives include carbonate, and they can help us to seal off the pores in the depleted zone. And to cap it all, I want to say our drilling design should be optimized enough to minimize problem without excessive cost. Okay, I'm not going to leave us in the cloud without helping us to know that some people have asked me what is the best tool for you to use for geomechanics. I didn't start my geomechanics practice from Alibotin. I started from Shell, and in Shell, I started using a different software from RockDoc, from DrillWorks. But over time, I've used like four different softwares for wellbore stability analysis, and I can tell you my preference today is DrillWorks. And these are the following are the strength of DrillWorks. DrillWorks has a centralized database that can coordinate all your models. So And the following are the things you can do with DrillWorks. You can do your seal analysis. You can do your geopressure prognosis. You can even do basin model analysis, geopressure. You can do Wellbore instability analysis. You can do your real-time. Is my most suitable software for real-time pore pressure Wellbore stability analysis. And you have your 3D view, your Explorer view that helps you to incorporate. If you have worked on different models across different feeds, all of them you can incorporate and integrate results from them to now have a robust geomechanical model. So if you are thinking of which software to use, please think of DrillWorks Predis. Thank you.
Thank you very much, David, for this wonderful and insightful presentation. I can say
Thank
that
you, sir.
You have defeated Goliath the second time if this has been a wrestling competition. It's not on a lighter note. Without wasting much time, I want to call on the chairman of this occasion, Engineer Joshua Dalla, to quickly give us a recap, because I see some exciting comments in our chat section, so that we can quickly go and look at them because of time. So, Chairman, sir.
Right. Thank you very much, David. What a beautiful and professional presentation. One of the best I've seen recently. So educative, with the most recap. So I understand you're doing your PhD. So that's actually great presentation. So let us go through the recap and see what David was addressing for us in case you can read. Here we're trying to look at how to address Wellbore instability in our drilling practices. David went ahead to introduce what Wellbore instability is. It says that on desirable conditions of an open hole interval in which the hole do not maintain the size and shape. And then he also mentioned the causes of Wellbore instability, which of course include two main aspects, which are the uncontrollable factors and then the controllable factors. He stated that for the uncontrollable factors, we have the naturally fractured formation, fractured and pocket formation. We also stated that we also have institute earth stress. We also have the pore pressure, and then so on and so forth. Then he also mentioned that the controllable factors are the bottom hole pressure. You can control those ones. The more density, you can control it. More chemical mixtures, and then the temperature, the pressure. All these are the factors that you can control. But he also mentioned that Wellbore instability attributes 44% of drilling and non-productive time. That is very important. I think we should note that. But he also stated that Wellbore instability is an offshoot of geomechanic studies, which of course is very critical to preview exercise that needed to be done in order for us to achieve optimal drilling operations, because it will help us to optimize our drilling, it will help us to control our sand production, it will also help us to fulfill the integrity of our well. A lot of the applications, of course, involve our ability to also carry out what we call the well for stability analysis, for which he stated that what we need to do, you need to build a model, you need to analyze the model. And in building the model, he said we should ensure that critical factors are considered, for which he mentioned the various stresses that you're going to encounter, and as well going ahead to analyze the model, and then from there you can now start your prediction exercise. Okay, so he went ahead to state that give us an overview of the mechanical model that we have, and then he emphasized the need for proper pressure distribution across the Wellbore formation. He stated the benefits of Wellbore analysis, which includes our need to understand the rock properties, rock stresses, and then the pore pressure in the building area, and also carry out pore pressure prediction in the Wellbore, as well as minimize costly non-productive time, which is very critical. Again, he gave us a case study where 4 wells were lost out of 10 wells that were drilled, and then the wells were highly deviated wells. And that the investigation carried out showed that the Wellbore stability analysis indicated SFP was higher than applied mode weight. Then they recommended that the deviated well should be properly analyzed, and it was performed, the analysis was performed, and then building was successful. He also stated that, and give us diagnosis of Wellbore failure. And then finally, he gave us recommendations and conclusions. And in the recommendation, he says that Wellbore stability analysis should be performed as a standard part of drilling pre-drilled modeling. I also agree with him on that. We know that as far as we're concerned, after all the studies, after all the de-risking, at the end of the day, you have to drill the well. And that is where the success is confirmed. So if you're going to have a discovery, you have to drill the well. And therefore, you have to be sure that you reduce the uncertainty. Most of the time, even if you do a proper de-risking of your exploration activities and studies, and then the challenges come when a client, or let me say operators, just go ahead and commence drilling without what we call pre-drilled geomechanical studies. We have discovered, especially in my company, energy and staff, energy strategies that our pre-drilled geomechanical studies is very critical in our drilling operations. So we recommend that to our clients that our drilling, pre-drilled geomechanical studies should be carried out for various wells. And in fact, David made us understand that there are no 2 wells that are the same. So of course, trajectories are going to change. Therefore, it is important that you carry on your pre-drilled geomechanical studies for all your wells before you commence the drilling operation. And that way we'll be able to tell you what you're going to encounter. That is what David is trying to bring to us. And he recommended some tools for us, which is GWalk, a proprietary of Halliburton. And we know Halliburton, they are also not others quite all right, but that is the recommendation. We also recommend that. So thank you very much, David, for this great work. I'm sure some of us who have been attentive, we have questions, so we can go ahead and ask our questions. Thank you, David.
Thank you, sir.
Very much, Mr. Chairman. And also, David, once again, thank you so much for that wonderful presentation.
Thank you, sir.
Okay, so we are in the interactive section now. I told you, David, that this topic is very interesting and you aroused a lot of interest in the participants. So we have lots of comments, about 18 of them in the chat section. But we want to see how we'll be able to tackle them. So the first one that I have to read for you is from Uchechukwu Fortune Ikene from University of Calabar. And the question is, what does it mean if the reservoir starts producing sand? So I don't know, is it that you'll be tackling the one after the other, you want to have all
I don't know
if
we can be having like 2-3 questions together, then attend to them, then we'll have the next set of questions.
Okay, that's fine.
Okay, while you are looking for the other question, let me just briefly attend to his question. What we mean by reservoir producing sand is your question, right? So we are talking about a state. The objective of production is to produce hydrocarbon. You want to flow out hydrocarbon, and you don't want it to come with sand. The sand particles, the matrix of the rock. You don't want them to flow with the fluid, the effluent that you are bringing to the surface. But it will get to a place as you are producing and the hydrocarbon is flowing into the wellbore, into the completed well, as a result of erosional activities, just like what you have in when the rain falls and you now have it as the water is flowing, it carries along with it some sand debris and it brings it and go and deposit it in gutters around us. Something similar like that is what we are talking about. A situation where you now have your crude now carrying along with it sand particles. The reason why we don't want this is as those sand are being transported from the reservoir to the surface, they are rubbing on the tubings. They are rubbing on the completion accessories downhole. And as they creep rubbing on it, it will get to a state that they will create a hole. And when they create a hole in your tubings, it means you now have downhole leakages. And when you are beginning to have downhole leakages, your pressure will not be effective again to bring up the hydrocarbon to the surface. So we don't want it in oil and gas exploration. I don't know if that answers your question enough.
Okay, so for the other 3 questions, I want to give you straight ahead, David. One, by the name is not complete yet. We said that what is the typical stress regime in the Niger Delta? That is one. The second question is by Emily Jamie from University of Calabar. He said the thing is cold collapse problem can become quite severe if weak binding plates intersect a wellbore at favorable angles. So what do you advise we do to avoid this collapse? So the third question by the same Olalekon, he says that, please, how do we account for stress changes as a result of fault reactivation in pre-drill geomechanics for Infill well?
Okay. Let me start from the first question. The person that asked what is the typical stress regime in Niger Delta, I mentioned it, maybe the person skipped it. The typical stress regime is Niger Delta is normal stress regime. So we are in a normal stress settings. Okay. How do we account for fault reactivation? For you to account for fault reactivation with a geomechanical model, fault reactivation is something that happens, that takes place over time. So when time is introduced into any model, it now goes into what we call 4D modeling. Because you are not looking at it in the X, Y, Z direction again, you are introducing time constraint, looking at it that, oh, what happened from time A and between time A and time B, that your fault now begin to reactivate. So accounting for fault seal reactivation, it's a question that will be answered by a 4D geomechanical model. If it's asking what can lead to fault reactivation, then I can throw a bit of light into it. I mentioned it that when you begin to do an injection into your reservoir, you can inject such a way that if you inject beyond the strength of the fault zone, because what it makes our faults to start sealing is what the geologists call this shade smearing. So it's like a wounded skin. So if you now begin to inject into it and it's not beyond the strength of the fault zone, you can reactivate the fault. Even your drilling activities can induce seismicity. But what can help you to account for it is a typical 4D geomechanical modeling. Can you please help me with the third question? I didn't get the question quite clear.
So I have 2 more questions. I think so. Okay. The third question is asking about, please, how do we account for stress changes as a result of fault reactivation? I think that's the last one you answered now.
Okay, so that means it's the second question.
Okay. So there is a question now by the same Yinka Olayinka from the University of Ibadan. He says, in view of the energy transition agenda, which the Nigerian oil and gas industry needs to take seriously, his question is this: that according to many schools of thought, the CCS, which is the carbon capture and sequestration, is the best option for transitioning in the most sustainable manner, and because depleted oil and gas reservoir as well as infrastructure are readily available. So will you kindly explain the significance of geomechanical evaluation and pore pressure response in situ stresses in preventing induced hazards like induced seismicity and fault reactivation during carbon dioxide injection? Furthermore, what energy-related actions is Nigeria taking?
Okay.
So I want to just dwell only on this before I give you the second question.
All right. Okay, let me just quickly answer his question. His question summarily is, what is the role of geomechanics in CCUS, carbon capture? Okay, if you are going to, your earth model is your storage tank. I want to explain it in a layman's term. If I have a tank and I don't know the strength of the tank, and I don't know what it can take, and I'm just pumping into it, it's like taking my tire to vulcanizer and I did not check the pressure rating of that tire material. I will pump it to a stage that the tire will explode. So if we don't do, the place of geomechanical modeling is to help analyze the subsurface, the strength of the rock, the seal, the strength of the, okay, the strength of, and this person is Mike, please. Okay, we want to analyze the strength of the seal material. We want to analyze the reservoir properties such that when we begin to inject CO2, carbon monoxide and all that into a depleted reservoir that he is suggesting, which is he has correctly suggested, we will not have what we call internal blowout. We will not have a situation where we will not fracture the seal, and that all the carbon that we are re-injecting into the subsurface now find its way back to the surface, or now go and contaminate another reservoir. If we are injecting into reservoir A, we don't want it to go and contaminate reservoir B above or reservoir C below it. So we want to know the strength of the rock, and what will help us also to account for this is 3D/4D geomechanical model, because our earth model is in 3 dimensions. Our earth, the subsurface is 3D. So we want to do a typical 3D geomechanical model, and we want to do, maybe we want to look into finite element model. This is similar to what I'm doing currently for my PhD. And you want to look into that and look at it that, oh, over time, after injecting into this reservoir for 10 years, for 20 years, how will it affect the sand? How will it affect the rock properties? How will it affect the rock strength? So that you can be sure that as you are injecting into it, the sand, the rock, the earth model have the capability to retain them, which is our objective.
Thank you very much. So we are making progress with some of the comments on the chat section. There is a question by David Jenny from University of Calabar, and we want to know that does loss calculation, or how does loss calculation rather relate to wellbore instability? Then the follow-up question, or rather another different question by Otuan Ekenyo from the same University of Calabar. So what are the disadvantages of using drilling mud in case of underbalanced conditions, and such as overpressured shield? That is the question again by Yinka Yinka.
So why not considering online questions?
It's just a commendation, just thanking you. All right.
Why not consider online questions, sir?
Yeah.
Okay. So the second question said, what are the disadvantages of using mud in underbalance? I didn't quite get what the person is trying to ask, but I don't know. In drilling, we drill over balance, except if intentionally you now want to drill under balance. And there are so many factors that can make one to plan to drill under balance. But it's asking for what are the disadvantages of using drilling mud in under balance scenario. So I don't get the thought pattern of this person. We want to drill over balance. And if you're asking what are the disadvantages of using drilling mud in its entirety, okay, I can say, okay, the reason why we watch what type of mud when we are drilling, what type of mud do we use when we are drilling into the freshwater zone, is because we want to avoid contamination of the freshwater zone. So when we drill that, we drill with water-based mud and oil, not oil-based mud. So now we are not just talking about all drilling mud in lump sum. We are looking at a particular type of drilling mud. But when you are drilling the deeper zones, because of reaction between shale and your mud, so you want to drill with oil-based mud to help you prevent what we call gumbo shale from swelling. We call it shale swelling. So because you are trying to avoid shale swelling, you need your oil-based mud. Some instances, you want to even use carbonate mud because of the reactivity of shale. But if he's asking what are the disadvantages of using drilling mud in its entirety, I don't think I get his question. But if he's saying, oh, he doesn't, what type of mud should be used to drill the freshwater zone so that we don't contaminate our subsurface, I'll say, okay, we'll use water-based mud because that one will not contaminate our subsurface. Can you please help me with the first question you raised again? I think I lost the question.
Okay, David, the
yes, sir.
questions on the chat box are much, and we want to say here that many of those questions, what we are going to do as a chapter, we are going to make sure that these are on the chat box and chat section that we are going to respond to them, especially those ones that have to do with the UNICAP. The coordinator here will find a way to submit those responses to them. Yes, so as more as they have the chance now, we should keep typing them on the chat box. But I have the last question that I want you to respond from Dr. So I want to read the question for you from David Ochaba. He said, considering the number of wells drilled and the production figures available in the Niger Delta, he said, do we have a growth model for the basin that can be fine-tuned on a field-by-field basis, which will be very useful for initial predictions of the required hydraulic properties?
Okay,
So
do we have?
Respond to this as the final question.
Okay, if I get this question clear, his question is to say, Niger Delta Basin has been penetrated by several wells, and do we have an existing model that have been? Okay, you are raising your hand, sir.
Let me go.
Okay,
Go ahead.
and
Go ahead.
the question now.
Go ahead.
All right, sir. So the question now is, do you have an existing model that covers the entire Niger Delta? The answer is yes. DPR, in conjunction with all the oil company, the IOCs, contracted Icon Science, and Icon Science did a studies on pore pressure prediction that covers 80% of the basins in Niger Delta. But like I mentioned, if you are looking at it from the angle of pore pressure, overpressure zones, we have information that covers, like, let's say 60% of it. We are not drilling, so maybe if we are drilling a well and we are drilling to like 20,000 feet, I don't know of any well that's gotten to 20,000 feet in Niger Delta anyways, and we are going to 20,000 feet, maybe the first 15,000 or the first 17,000 feet of it has been penetrated before. The remaining 3,000 feet becomes exploratory. So we need to account for that. That is number one. But like I mentioned, even if you know the pressure regime, even if you know the magnitude of the overpressure, no two wells have the same trajectory, and they will not behave the same way. That was why I displayed this Spheronoise plot in my presentation. The Spheronoise plot shows us that if you change the inclination and the azimuth, which always changes, if you change the inclination and the azimuth of your well, you have to analyze for Wellbore instability. And until you do this, you will not know the appropriate mud weight to use. If you do anything otherwise, what you are doing is a best guess. And considering the amount of money that goes into drilling, we should not be doing guesswork in drilling. We should rather build a geomechanical model that give us base that incorporate and integrate all the well information. The well spoke to us while it was drilled. We don't build a geomechanical model by just looking into the sky and using one and doing abracadabra. What we do is that we analyze the drilling reports, daily drilling report, end of the well report, and we look at why did the well fail. An engineer may look at it from an engineering angle, but a geomechanical model will look at it from both the engineering and the geology angle and integrate all the available informations together, and will come up with a robust geomechanical model that will give an answer that, if followed, it will drill without any instability issue.
Okay, thank you very much, David. That is a very, 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 very important question. Thank you, David.
Thank you, sir.
And just like you said, critical, there is no two wells that have the same trajectory. Most of the time, operators tend to assume that, okay, since I've built this well, let me just go ahead and deal with the same data. It doesn't work like that. Yeah, it doesn't work like that because if you assume certain pore pressure, for example, somebody can assume the pore pressure of 1. We have seen situations whereby you now go ahead and deal with those mud weight, and if that's not all the wells, you will have to be very careful. Like you said, the various trajectories are changing as you drill. If you drill probably maybe on the let's say northwest trajectory, or maybe if you are drilling over and underneath water maybe let's say seabed. You can see that all of these, your overburden will also change as well. Because in all of these, you also need to know that the water density also changes and depth. So these are areas that you want to consider, and therefore you need to be very, very careful to avoid assuming that because you are successful in the some of the infill wells, and that's the question I wanted David to throw light on. Therefore, you will be successful in all. It is better to fill each well as an individual well, and also carry out the reduced geomechanical study separately. And that's a great answer, David. Thank you very much for that.
Thank you very much, the chairman, and also David, for your responses. One last final question, David, please, before you go. From Dr. Emmanuel Maduawa, he said, kindly give more insight on the aspect of fault zone causing well instability. Is any estimated real cost implications to companies? So this is the final question for you for this section.
The last sentence, please. You said, kindly give more insight on fault zone causing Wellbore instability. Then what is what you said again?
Any estimated real cost implications to companies?
Okay. Fault zones are weak zones. My geology taught me that when you are drilling through a fault is a zone, like you rightly mentioned, is not a line. So it means all that interval is weak. When you are drilling it, it means all the rock fragment around that interval, that zone, has been broken into pieces. They are just gummed to each other by the adjoining stresses in the abandoned rocks. So if you now go there and you remove one of it, it means they can just be falling on each other and falling into the well. So if you are drilling into fault zones, they are already, because it's a weak zone, it can be falling on you and it can pack off. It can cause what we call whole collapse and pack off. Whole collapse, pack off, resulting to well control issue, Wellbore instability issue. Is asking any estimated cost because it's to infinity. I can't say this is the amount that it can cost. For example, it depends on how long the company stayed trying to resolve the issue before taking decision. Let's say, for example, if the company stays there and they say, oh, let's try and see if we will be able to fish and be able to bring the BHA out of O. And they are there for 20 days. The 20 days, the rig owner is counting days. The rig rate times 20. It's not the same for a company that now decide to say, oh, we are going to stay there for 2 days. And apart from that, apart from them not deciding to sever the well, they may be having issues with the regulators. If they have radioactive substance down O and the regulators are not giving them permits to say bury the radioactive substance, they can be there for days until they get the permit and the clearance to say, oh, you can bury the hole, they cannot sever the well. That's number 2. Number 3, that can be a challenge in such a situation is the servicing company that is providing the BHA will estimate the cost of their BHA, and they will get back to the producing company to say, you buried our BHA down hole, we need our money back. So all these things culminate into each other and it runs into millions of dollars. So I can't give you a fixed amount, but you may want to consult literatures of what people have done, research that people have done, and the figures that they have put there. But we know that it causes loss of a cost economic problem. It infringe into our well costs, and we don't want that. What we want is to optimize our costs.